Okay, so I want to start today just by reviewing really quickly a little section at the end of chapter 21 that I don't think I talked about last time, which is sometimes you'll see Coulomb's law written in a more technical vector form. Your book writes it this way, that the force is equal to the electrical constant times the product of the charges times the distance between the two points, which they're calling here R21 squared, times a unit vector in the direction that points from point 2 to point 1. So force is a vector. The thing that it's equal to has to be a vector, and the thing that it's equal to is the product of the charges divided by the distance squared times a unit vector in that direction. Sometimes you'll actually see this equation written in advanced E&M books slightly differently. You'll see, for example, the electric field sometimes written as 1 over 4 pi epsilon naught, which is how we write the electrical constant usually in more advanced texts, times the product of the charges, so Q1 times Q2, times the vector that goes from one charge to the other divided by the magnitude of that vector cubed. And that may look strange, that may look like a 1 over r cubed law and not a 1 over r squared law, but this is the vector that includes the direction, and this is dividing that by the magnitude of the vector cubed. So what you get is essentially the magnitude of the vector squared times a unit vector in that direction. So if you ever come across the equation for the electric field or electrical force that it looks like a 1 over r cubed law, keep an eye out for this vector in the numerator. If it's not a unit vector, if it's a unit vector, then you'll have 1 over r squared. If it's the full radial vector that points from charge 1 to charge 2, then you might have this 1 over r cubed. So this is the vector, the magnitude and the direction divided by the magnitude cubed. And sometimes, again, you'll see that in more advanced electromagnetism texts. So we want to talk about the electric field, and we've said a couple of times that we can view electrical forces as being due to electric fields, where the electric field of a point charge is equal to 1 over 4 pi epsilon naught times the charge divided by the distance between the charges squared, and then the force experienced by this charge in that electric field is going to be equal to its charge times the strength of the electric field at the point in space where it finds itself. By convention, we draw electric field lines pointing away from positive charges and towards negative charge. So if this charge Q was a negative Q, then the electric field lines would point this way towards the charge, and all of the vectors, the electric field, would be in the opposite direction. So by convention, the electric field lines, the direction of the electric field lines show you what direction a positive charge would experience a force in that electric field. So the electric field for point charges is just given by Coulomb's law. If we have many objects creating an electric field, for example, suppose we had 3 charges, charge 1, charge 2, charge 3, and we wanted to know what the electric field was at some point in space due to those 3 charges. The electric field is just the sum of the electric field due to charge 1 and the electric field due to charge 2 and the electric field due to charge 3, and these are all vectors, so obviously this sum is a vector sum. But we can write that the electric field at some point in space is equal to the sum over I, where I is the various electrical charges that contribute to that field, of the electric field due to each individual charge. And we sometimes refer to that as the principle of superposition. In other words, the field at any point in space is equal to the superposition of the fields caused by any one of the individual charges. If instead of just a bunch of point charges, you've got some sort of, let's just erase all this, continuous distribution of charge in space. You've got some sort of object with some three-dimensional shape that has some charge, and you want to know what is the electric field at some point in space due to that object, well then instead of adding up the finite contributions to the electric field of all the finite bits of charge that make this up, then the electric field is equal to the integral over that object of the electric field due to each, it's not very legible, sorry about that, the electric field due to each little bit of charge divided by 1 over 4 pi epsilon naught r squared. In other words, to find the electric field due to a continuous distribution of the charge, you have to integrate over all of the little bits of charge dq that make up that continuous object, and you integrate that either over the volume or the area or whatever the shape is of the object that you are finding the electric field of. The next few problems we'll be looking at the electric field of extended objects, objects like lines and disks and loops of charge, and we're going to look at various ways to integrate over the electric field of the individual pieces of that charged element and add them up to find the total electric field. This procedure would theoretically work for any electric field of any object of arbitrary shape. Obviously, doing this integral could be complicated if the shape was complicated, if the distribution of electrical charge was not uniform. This integral might be very hard to do. So what we will focus on is the electric fields of objects that have a high degree of symmetry, that are geometrically simple, and that we can find the electric field without too much complexity. So for the next videos, we'll look at a disk of charge, then we'll look at a line of charge, and then we'll gradually make those shapes more and more complicated.